let us discuss hyperfine splitting and hyperfine structure in spectra. Hyperfine structure in spectroscopy is the splitting of spectral lines into a number of components. The splitting is caused by nuclear effects and cannot be observed in an ordinary spectroscope without the aid of an optical device called an interferometer. The splitting of ESR spectra of an electron by the interactions between the magnetic spinning electron and the adjacent spinning magnetic nuclei is called hyperfine splitting, and the resulted splitting ESR signals are called hyperfine structure. It arises from the interaction between the magnetic moments of the nuclear spins and the magnetic field generated by the electron spins, leading to further splitting of spectral lines. The hyperfine splitting refers to the phenomenon in ESR in which a single peak is split into multiple lines due to the interaction between electron spins and the magnetic nuclei in the sample. The splitting is determined by the quantum number of the nucleus and provides valuable information for identifying radicals. Origin of hyperfine splitting. Hyperfine splitting occurs due to the interaction between the magnetic moments of the nucleus and the electrons, which are in the immediate vicinity of the nucleus. This interaction, also known as hyperfine coupling, is analogous to the spin-spin coupling, J coupling, that is in NMR. The magnitude of this interaction is characterized by the isotropic hyperfine coupling constant denoted as small a. Impact on NMR spectra. Hyperfine splitting results in the further splitting of NMR signals or peaks into multiple lines. The number of lines and their intensities follow a pattern based on the number of equivalent neighboring nuclei with non-zero nuclear spin I. The splitting pattern is described by 2Ni plus 1 rule, where Ni is the number of equivalent neighboring nuclei with spin I. The intensity ratio of the split lines follows Pascal's triangle, similar to spin-spin coupling in NMR. Examples: a hydrogen atom with a single proton, the spin of the nuclei I equals 1 by 2 will show a single peak in its NMR spectrum. But if it is interacting with the neighboring nucleus with spin I, the peak will be split into doublets. So it will appear as two lines. If the hydrogen atom is interacting with two equivalent neighboring nuclei with the spin I equals 1 by 2, then the peak will be split into triplet, 3 lines. Distinction from fine structure. While hyperfine splitting is a result of nuclear spin-electron spin interaction, fine structure arises from the interaction between the electron spin and its orbital motion, spin-orbit coupling. Hyperfine splitting is a smaller effect than the fine structure and is observed in high-resolution spectroscopy. Applications. Hyperfine splitting is a valuable tool for determining the number and the type of neighboring nuclei that are interacting with the observed nucleus. It can also provide information about the electron structure of molecules, particularly radicals, in electron paramagnetic resonance spectroscopy. Number of peaks in ESR and the selection rule. In general, if a single electron interacts magnetically with n equivalent nuclei, then the electron signal is split into 2Ni plus 1 multiplets, where n is the number of nuclei, I is the spin quantum number of the nucleus, which is equal to 1 by 2. For example, we take a hydrogen radical. Here n equals 1, number of proton is n equal to 1, and I equals 1 by 2, which is spin of the nuclei, and number of signals will be 2Ni plus 1. We'll have to use this formula. So 2 multiplied by 1 multiplied by 1 by 2 plus 1, that will give us 2. So the experimental spectrum will be 1:1. For methyl radical, N equals 3. So we are going to leave the carbon and we are going to take only hydrogen atom into account. So N equals 3 and your I will be 1 by 2. Number of signals will be 2 multiplied by 3 multiplied by 1 by 2 plus 1, which is equal to 4. So using 2Ni plus 1, we have I equals 1 by 2, we have 4 transitions. It means ESR spectrum contains 4 equally spaced lines, quadrant. So the experimentally observed pattern will be 1:3:3:1. We will see later how the intensity rises into 1:3:3:1. The selection rule for hyperfine transition is del ms equals 1, del mi equals 0. ESR spectra of free radicals in solution. Hyperfine spectra of free radicals in solution. The ESR spectra of free radicals in solution are very much useful for getting details of electron distribution and the structure of the radicals. The free radicals must be produced in a concentration of about 10 to the minus 13 mole per meter cube for getting a good ESR spectrum. ESR spectrum for hydrogen free radical. For a hydrogen radical, where S equals 1 by 2, I equals 1 by 2, so we have Ms equals plus or minus 1 by 2 and Mi equals plus or minus 1 by 2. In the absence of magnetic field B equals 0, the electron spin energy levels are degenerate. So we are going to apply the magnetic field Ms equals minus 1 by 2, sublevels going down, and Ms equals plus 1 by 2 and sublevel going up. So which is shown in the diagram. So this is the diagram we will see now. ESR spectrum for hydrogen free radical. For each electron sublevel interacts with the nucleus, Mi equals 1 by 2 and minus 1 by 2, giving 4 sublevels designated by the value of Mi. This is called hyperfine interaction. On passing microwave radiation into hydrogen atom, 2 transitions are possible as per the selection rule. Del ms equal to plus or minus 1, del mi equals 0, resulted 2 ESR lines, a doublet as shown in the diagram. The 2 ESR lines are equally intense. The spacing between them is called hyperfine coupling constant, which is denoted as A, expressed in Tesla or millitesla units. So you have now Ms equal to plus or minus 1 by 2 when there is no magnetic field applied. So these are degenerate levels. The moment when you are going to apply magnetic field, then this line split into Ms equals plus 1 by 2 and Ms equal to minus 1 by 2. And the difference between these two is nothing but del E. And further, when it interacts with the magnetic moment of the nuclei, and this line is split into further plus 1 by 2 and minus 1 by 2, and this line split into minus 1 by 2 plus 1 by 2. And these 4 lines are called hyperfine. So hyperfine structure. And we'll have to follow this rule, selection rule, del Mi equals 0. So that's a transition between minus 1 by 2, minus 1 by 2, so del Mi equal to 0, and plus 1 by 2 to plus 1 by 2, where del Mi equal to 0. And this is the experimental spectrum that we have obtained. So we have, and the distance between these two peaks is nothing but hyperfine coupling constant A, and we have 1:1. So intensity is nothing but 1:1. So for any hydrogen radical, we have the intensity ratio is nothing but 1:1. And this is referred the same picture we have drawn neatly here. And we have 2 transitions using selection rule del Mi equal to 0. These 2 transitions, where we have 4 lines. After the electron interacts with the magnetic moment of the nuclei, we have hyperfine structure. And this is one more picture, the same picture. It has been drawn nicely. So this is a degenerate state when you're going to apply magnetic field, and this line is split into alpha state and beta state. There's a separation, and when this electron interacts with the magnetic moment of the nuclei, again they split into 4 lines. So we have 4 lines here, but the transition lines and these 2 blue lines only, they will, obliging selection rule will give us transition. So we have 2 intense lines, 1:1. ESR spectrum or hyperfine structure for methyl radical. On passing microwave radiation into CH3 system, the 4 transitions are possible, and the selection rules are del ms equal to plus or minus 1 and del mi equals 0, resulting 4 ESR lines called quadrant. For CH3, S equal to 1/2, we have ms equals plus 1/2 and minus 1/2. Since for proton, I equals 1/2, so we have taken only hydrogen. So we are going to leave the carbon atom here. And we have mi values for 3 equivalent protons are given as mi equals plus 3/2, plus 1/2, minus 1/2, minus 3/2. So we have 4 lines. In the absence of magnetic field B equals 0, then electron spin energy levels ms equal to plus or minus 1/2 are degenerate. And in the presence of magnetic field, when B is not equal to 0, we are going to apply the magnetic field. Then the electron energy level ms equals minus 1/2 going down, and the spin energy level ms equal to plus 1/2 going up, as shown in the figure. So we have now, and this is for CH3 radical degenerate value. The moment when you're going to apply the magnetic field, this line split into 1/2, 1/2 plus 1/2 and minus 1/2, and further this line, when the electron interacts with the magnetic moment of the nuclei, split into four lines, and here also we have 4 lines. So starting from plus 3/2 minus 3/2, so plus 3/2 plus 1/2 minus 1/2 minus 3/2. Similarly, we have also this line ms equals minus 1/2 is split into 4 lines, and we have the transition obliging the selection rule del mi equals 0. So we have 4 intense lines. So this line minus 3/2 minus 3/2, and this will be minus 1/2 minus 1/2, and you have plus 1/2 plus 1/2 and plus 3/2 plus 3/2, and this is our hyperfine structure. And what are the experimentally observed spectrum? So we have now 4 intense lines, and these 2 lines are the peak values will be 3 times of the original one. So 1:3:3:1. So we have 4 intense lines. ESR spectrum contains 4 equally spaced lines, that is quadrant. And this is again one more the same picture, and this distance is nothing but hyperfine constant, a hyperfine coupling constant, this small a, peak to peak, and this is equally spaced and with the ratio 1:3:3:1. ESR spectra of hydrogen radical. The hyperfine splitting is explained using ESR spectra of hydrogen radical. In hydrogen radical, odd electron is present. Hence, for the hydrogen, unpaired electron. Hence, it gives ESR spectra since it has an odd number of electrons, and it is magnetically active nuclei. Nuclear spin of proton H equals I equals, for proton I equals 1/2. Number of protons is nothing but n equals 1. So this hyperfine splitting is going to cause the ESR signal into 2ni plus 1. So we have 2 multiplied by 1 multiplied by 1/2 plus 1. We have 1 plus 1, which is equal to 2, and the signal intensity will be 1:1. This is a doublet line. Hydrogen radical gives doublets in ESR spectra. And this is exactly pictorial of ESR spectra of free radical hydrogen radical, and in the absence of a magnetic field, we have degeneracy level, and the moment when you are going to apply the magnetic field, this splits into ms equals minus 1 by 2, and this is the direction is exactly matches with the external magnetic field, and we have both the directions, ms equals minus 1 by 2, and the external magnetic field in the same direction, and we have higher energy ms equal to plus 1 by 2, that's split into two lines, and this ms equals minus 1 by 2 also split into two lines, and we have the experimentally observed spectrum will be 1:1. We have two peaks here, and dA by dB versus B. So this is a gradient of magnetic field B, and A is nothing but your absorption spectrum. So in hydrogen radical, I equals 1 by 2. So we have Mi equal to plus or minus 1 by 2. So there are two transitions possible. One is plus 1 by 2 to plus 1 by 2, and minus 1 by 2 to minus 1 by 2. So that's why we have observed two signals doublets. Now ESR spectra of methyl radical CS3, and we have 1:3:3:1, which is nothing but the intensity of the experimentally observed spectrum of methyl radical, and we have four lines, four intense lines, the first line, and three times of the second one, three times of the first one, and again the same original one. We have 1:3:3:1. Magnetically active is nothing but hydrogen. The number of proton is nothing but n equal to 3, and the nuclear spin 1 by 2. Substitute in the hyperfine splitting rule. We have four intense lines, quadrate. This is pictorial representation of methyl radical, and we have four intense lines, four possible transitions. One is plus 3 by 2 plus 3 by 2, 1 by 2 2 plus 1 by 2, minus 1 by 2 minus 1 by 2, minus 3 by 2 minus 3 by 2. And this is the experimentally observed spectrum. So 1:3:3:1. Now let us learn G factors in ESR spectroscopy. In ESR spectroscopy, the G factor is a proportionality constant that relates the magnetic moment of an electron to its spin angular momentum with a value of approximately 2.0023 for a free electron. The G factor, often denoted as G, is a scaling factor used in electron spin resonance spectroscopy to account for the coupling between an electron spin and orbital angular momentum. It's crucial for understanding the energy levels of electrons in a magnetic field and is analogous to the chemical shift in NMR spectroscopy. The G value is not a constant, but a tensor quantity that can be affected by the electronic environment of the unpaired electron. G value in ESR spectroscopy is an important parameter that helps to characterize paramagnetic substances. By measuring the magnetic field strength required to observe resonance at different frequencies, the G value can be derived using the equation G equals h nu over mu b del b, where h is the Planck's constant, nu is the microwave frequency, mu, this is suffix b. It is not multiplied by b. This is mu suffix b. Mu suffix b is the Bohr magneton, and del b is the magnetic field difference between the resonance peaks. In free radicals and some ionic crystals, the G value is closer to the free electron value, which is 2.0023. In other systems, such as transition metal complexes, the G value can be significantly different, depending on the electronic structure and the environment. The G tensor arises from the interaction of the electronic spin with an external magnetic field, and it plays a similar role to shielding in NMR. The G factor is also referred as Landé G factor. Interpretation of Landé G factor, Landé splitting factor. The energy difference between two spin states is given as del E equals h nu, which is equal to G beta h, and we can calculate G, which is equal to h nu by beta h, where G is a spectroscopic constant or the G splitting factor. The expression for G is given as this expression: G equals 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2J times J plus 1, where J equal to L plus S, we know already. So, for example, if we take a free electron and N equals 1 and S equal to 1 by 2, and at the ground state we have L equal to 0. So we have J equal to N plus S, that will give us 0 plus 1 by 2, J equals 1 by 2. Substituting all the values in this expression for G, we have 1 plus 1 by 2 times 1 by 2 plus 1 plus 1 by 2 times 1 by 2 plus 1 minus, where L value is 0, so 0 times 0 plus 1 divided by 2J, J plus 1, that will give us G equals 2. So this is the theoretical value. Whereas in the experimental side, the free radical is given as, is obtained as 2.0023. And 0.0023 is a relativistic correction. So we'll have to make the relativistic correction. So that's why this value differs from the theoretical value, and the difference is 0.0023. So relativistic correction. So there's a relativistic correction, so which is given as 0.0023. The above G value will not be applicable for metal complexes because the odd electron will be moving in a particular orbit. G value depends on crystal field splitting parameter and LS coupling. G factor in ESR spectra. The position of ESR signal is defined by the effective G value given by J equals h nu divided by mu B Bz. Since h and mu B, Bohr magneton, it is not Bohr magnetron, it's Bohr magneton, are constants. Hence G factor is a measure of the ratio between frequency and magnetic field. That is, G is directly proportional to mu divided by B. Factors affecting G value. For a free electron and organic radicals such as methyl radical, the G value depends upon the spin angular momentum of the electron itself, and its value is found to be 2.0023 GeV times. In the case of the transition metal ion, their complexes, G value depends upon the spin and the orbital motion of the electron, so that G value departs from GeV value. So we have the graph between dA by dB, which is the gradient of absorption, gradient magnetic field with absorption, and we have B here on the x-axis, where it cuts the x-axis, that will give us the value G. In solution, because of a free rotation motion, G factor is isotropic, that is, it is the average of the G value in the x, y, z directions. In solid state, because of restricted motion, the G value is anisotropic, that is, its magnitude depends upon the direction of measurement. Hyperfine splitting. Interaction of electron spin and the nuclei with the magnetic spin. If radical contains n equivalent nuclei with the spin quantum number I, then the quantum number of hyperfine lines will be 2ni plus 1. When the splitting is caused by both a set of n equivalent nuclei of spin I and a set of m equivalent nuclei of set of ij. So this is your ii and this will be your ij. Then the number of lines will be 2nii plus 1 times 2mij plus 1. And the corresponding picture for the hydrogen atom for the hyperfine splitting is given as, for I equals 1 by 2, ms equal to plus or minus 1 by 2. So we have the selection rule. So using the selection rule, del ms equal to plus or minus 1 and del mi equals 0, we have a degenerate level is split into ms plus 1 by 2, ms equals minus 1 by 2, low energy and high energy. And further, when it interacts with the magnetic moment of the nuclei, we have another two lines, and we have another two lines. So we have transitions between these two lines. Using transition between these lines, we have two intense lines for hydrogen atom. Using this del m is equal to plus or minus 1, and del m using this selection rule, del m equal to 0. So we have two signals, two intense lines, these two signals, which is nothing but 1:1.